Namaste, my friend, and welcome back to JEE Chemistry with Typical Monk. This is class 11, and today we step into a chapter that quietly runs half of inorganic chemistry, ionic equilibrium. Here is a question worth sitting with. Why does a lemon taste sour and soap feel slippery on your hands? And here is a stranger one still. Why does pure water, sitting all by itself, quietly split a tiny fraction of itself into ions? Sarah once asked exactly this, and the answer she got back was one word: balance. Behind the sourness, the slipperiness, and even that quiet splitting of water sits a single, elegant equilibrium. And in JEE, this one balance grows into multi-step numericals on buffers, salt hydrolysis, and solubility. Today, one idea at a time, let us build it from the ground up. Take a slow breath. Let us begin. So what will you carry home from today's class? First, 3 views of the same idea: acids and bases through Arrhenius, through Brønsted and Lowry, and through Lewis, each one wider than the last. Second, KWPH and POH, the ionic product of water, and the ruler we use to measure acidity itself. Third, Ka and Kb, the common ion effect, and buff is built on the Henderson equation. Fourth, salt hydrolysis and the solubility product Ksp, the constant that decides whether a salt stays dissolved or falls out as a precipitate. And fifth, the JEE drills, a worked pH and buffer numerical, assertion and reason. Mash the column and more numericals. So today's ideas also become today's marks. Ready? One idea at a time. Let us start with the question that sounds almost too simple. What actually is an acid? The first answer came from Arrhenius. An acid is anything that gives H+ ions in water, and a base gives OH- ions. Clean, simple, and it explains most of school chemistry. But David once asked him, what about ammonia? It behaves like a base, yet it has no OH- sitting inside it at all. Arrhenius had no answer for that. So along came Brønsted and Lowry with a wider idea. An acid donates a proton. A base accepts one. Ammonia accepts a proton from water. So under this view, it is a base after all. No OH- required. And then Lewis widened it once more, all the way to electron pairs. An acid accepts an electron pair. A base donates one. This is the broadest view of all, and it is why even a metal ion with no protons inside can behave as an acid. And notice one more quiet thread running through all of this. Every acid, once it gives away its proton, leaves behind a conjugate base. The two differ by exactly one proton, always paired, like two sides of the same coin. Now, let us build the ruler chemists actually use. pH is defined as -log of the hydrogen ion concentration, and pH the same way for hydroxide, a compact scale running from 0 to 14 that turns an impossibly tiny number like 10 to the -3 into a friendly little number like 3. Lisa once said reading raw hydrogen ion concentration felt like reading a phone number, but reading pH felt like reading a clock. That is exactly the point of a logarithmic scale. The low 7 is acidic, exactly 7 is neutral, and above 7 is basic. Lemon juice sits down near 2, soap sits up near 9, strong sodium hydroxide climbs past 13. And here is the constant tying it all together. At 25 degrees Celsius, Kw, the ionic product of water, equals 10 to the -14, and that forces pH plus POH to equal 14. Always, no matter which one you are given. One last distinction before we move on. A strong acid or base dissociates fully, so its pH comes straight from concentration. A weak acid or base only partially dissociates, and exactly how far it goes is governed by Ka or Kb. Keep that difference close, because the next slide depends entirely on it. Now, for one of the most beautifully practical ideas in this whole chapter. How do you build a solution that refuses to change its pH? It is called a buffer, and its whole job is to resist a change in pH when someone adds a small amount of acid or base to it. John once poured a drop of strong acid into plain water and watched the pH crash. He poured the same drop into a buffer, and the pH barely moved at all. An acidic buffer is built from a weak acid together with its own salt. The salt supplies the conjugate base. A basic buffer flips that, a weak base together with its own salt. And here is why it works. That salt supplies a common ion, and that common ion pushes back on the weak acid's own ionization, holding it steady exactly where you want it. All of this collapses into one clean line, the Henderson equation, pH equals pK a plus log of salt over acid. Hold on to this equation tightly, because we are about to put it to work. Now the G twist, one weak acid, walked through twice, so you feel the buffer's power with your own hands. We start with 0.1 molar acetic acid alone, Ka equal to 1.8 into 10 to the minus 5, and then we add 0.1 molar sodium acetate to it. Step 1. The weak acid alone. For a weak acid, hydrogen ion concentration equals the square root of Ka times concentration. Square root of 1.8 into 10 to the minus 6, which is 1.34 into 10 to the minus 3 molar. That gives a pH of roughly 2.87. Step 2. pKa. pKa is minus log of 1.8 into 10 to the minus 5, which comes out to 4.74. Keep that number, we will need it in a moment. Step 3. Add the salt. Pour in 0.1 molar sodium acetate, and the common acetate ion suppresses the acid's own ionization. This mixture is no longer a plain weak acid. It is now an acidic buffer. Step 4. Henderson. P equals pKa plus log of salt over acid, which is 4.74 plus log of 0.1 over 0.1. That ratio is exactly 1, and log of 1 is 0. Step 5. The buffer pH equals 4.74 plus 0, so pH equals 4.74. Notice what just happened. The same acid jumped from 2.87 all alone to a gentle 4.74 once buffered. That gap, right there, is the entire power of a buffer in one number. Now a different kind of equilibrium, not an acid dissolving, but a salt refusing to dissolve any further. For a saturated, sparingly soluble salt, Ksp is the equilibrium product of its ion concentrations, a constant fixed at a given temperature, exactly like every other equilibrium constant we have made. Now take the same salt in any fresh solution and compute the same product from whatever concentrations are actually present right now. Recall that Q. Compare the two. If Q is less than Ksp, the salt happily stays fully dissolved. But add a common ion, say chloride, to a solution that already has silver ions, and Q climbs above Ksp, and a precipitate begins to fall out. This, once again, is the common ion effect, now working on solubility instead of on a weak acid. And here is the G link you must not miss. Solubility is derived from Ksp, never equal to it, for a salt of the type AB2. Ksp works out to 4s cubed, where S is the molar solubility. Learn that relationship once, and every solubility product numerical opens up. Now sit up straight. These 5 lines are what G actually asks, year after year. 1. At 25 degrees Celsius, Kw equals 10 to the minus 14, so pH plus pOH equals 14. Memorize this code, it should be faster than your own name. 2. For a strong acid or base, pH comes straight from concentration. For a weak one, you need Ka or Kb and the degree of dissociation. Never skip that step. 3. The Henderson equation pH equals pKa a plus log of salt over acid only applies to a genuine buffer pair, a weak acid with its own salt, nothing else. 4. The common ion effect suppresses ionization of a weak acid or base, and through Ksp, it also lowers the solubility of a sparingly soluble salt. The same idea, 2 costumes. 5. Salt hydrolysis follows the pattern strength. A weak acid salt turns basic, a weak base salt turns acidic, and when both patterns are weak, the answer depends on whichever of Ka or Kb is larger. Let us drill the G way. Remember the 4 options. Option A, both statements true, and the reason explains the assertion. Option B, both true, but the reason does not explain the assertion. Option C, assertion true, reason false. Option D, assertion false, reason true. First one, assertion. the solubility of silver chloride decreases in a solution of sodium chloride. Reason: the common chloride ion shifts the silver chloride equilibrium backward. The common ion effect. Check each on its own first. Is the assertion true? Yes, adding a common ion really does push the equilibrium back and lower solubility. Is the reason true? Yes. And does the reason explain the assertion? Perfectly. That shift backward is exactly why the solubility falls. Both true. Reason explains option A. Second one. Assertion: a buffer resists a change in pH when a small amount of acid or base is added to it. Whole water has a pH of 7 at 25 degrees Celsius. Both statements taken alone are true. But pause. Does the neutrality of pure water explain why a buffer resists change? No, not even slightly. Those are two separate facts standing side by side. Both true, but the reason does not explain the assertion. Option B. This is the trap that catches John every time. Two true lines that simply happen to sit next to each other. Third one. Assertion: an aqueous solution of sodium chloride is strongly basic. Hydrolysis, chlorium chloride, is the salt of a strong acid and a strong base. Check the reason first. Sodium chloride is indeed the salt of hydrochloric acid and sodium hydroxide, both strong, so the reason is true. Now the assertion: a salt of a strong acid and a strong base does not hydrolyze at all. It simply stays neutral, pH 7. So the assertion is false, and the reason is true. Option D. A quick match now. Say each answer aloud before I reveal it. The ionic product of water, Kw, 10 to the minus 14 at 225 degrees Celsius. The constant behind every pH calculation. Buffer pH, pKa plus log of salt over acid, the Henderson equation, straight from 2 slides ago. A salt of a weak acid and a strong base, a basic solution because the weak acid's conjugate base wins the hydrolysis tug of war. And the condition for precipitation, Q greater than Ksp. If all four came to you before the reveal, this chapter is becoming yours. Use a favorite G format. I will read some statements. You silently count how many are correct. Statement 1. The common ion effect suppresses the ionization of a weak electrolyte. Hold your verdict. Statement 2. Adding a common ion changes the numerical value of Ksp itself. Think carefully before you answer this one. Statement 3. At 25 degrees Celsius, the sum of pH and pOH is always 14. This one you have now seen 3 times today. So, how many are correct? 2 statements, the first and the third. The common ion effect truly suppresses ionization, and pH plus pOH truly always equals 14 at that fixed temperature. But the second one falls hard. A common ion shifts the position of equilibrium and changes solubility, but Ksp itself is a constant that depends only on temperature, never on which ions you happen to add. That distinction is exactly where G tries to catch you. Now let me save you some marks. 2 myths that trap thousands of students every year. Myth 1. The pH of any dilute acid can be found directly as minus log of its concentration. It feels so tempting. One clean formula for everything. No. But here is the truth. That shortcut only works for a strong acid, which dissociates completely. A weak acid must first go through its degree of dissociation. Alpha equals square root of Ka over concentration. And only then can you find the true hydrogen ion concentration. Skip that step, and every weak acid pH you calculate will be wrong. Myth 2. Adding a common ion increases the solubility of a sparingly soluble salt. After all, you are adding more of something. So surely more dissolves? No. The truth is the exact opposite. Le Chatelier's principle applied to a solubility equilibrium says the extra common ion pushes the reaction backward and solubility drops, not rises. This is the very common ion effect we met with buffers, now doing its work on precipitation instead. Time to test yourself, rapid fire, and today it is all numbers. Here is the rule. I ask, you answer in your head before the reveal, using exactly the formulas from today. Question 1. What is the pH of 10 to the minus 3 molar hydrochloric acid, a strong acid? Straight from concentration, pH equals 3. Question 2. If the pH of a solution is 4, what is its pOH? 14 minus 4, pOH equals 10. Question 3. What is the pH of a 0.1 molar weak acid whose kk is 1 into 10 to the minus 5? Alpha equals square root of Ka over concentration, square root of 1 into 10 to the minus 4, which is 0.01. Hydrogen ion concentration equals concentration times alpha, 1 into 10 to the minus 3, so P equals 3. Question 4. A buffer has pKa equal to 4.74, and the ratio of salt to acid is 10. What is its P Henderson? 4.74 plus log of 10, which is 1, so P equals 5.74. And question 5, the sharp one. Ksp of silver chloride is 1.8 into 10 to the minus 10, and it is dissolved in 0.1 molar sodium chloride, a common ion solution. What is its solubility now? Solubility equals Ksp divided by the chloride ion concentration already present, 1.8 into 10 to the minus 10 divided by 0.1, which gives 1.8 into 10 to the minus 9 molar, far smaller than in plain water, exactly as the common ion effect predicts. Let us gather the whole class in one slow breath. Acids and bases wear three faces: Arrhenius, Brønsted, and Lowry with the proton, and Lewis with the electron pair, and every acid leaves behind a conjugate base. Kw equals 10 to the minus 14, and pH plus pOH equals 14 at 205 degrees Celsius. pH itself is minus log of hydrogen concentration. Ka and Ab measure how far a weak acid or base actually ionizes, and the common ion always suppresses the ionization. A buffer's pH follows the Henderson equation, pH equals pKa plus log of salt over acid, and every salt hydrolysis according to the strength of its own parent acid and base. Precipitation begins exactly when Q exceeds Ksp. Solubility is derived from Ksp, never equal to it. And a common ion always pulls that solubility down. And next class, we turn to redox reactions, oxidation numbers, balancing equations by the ion-electron method, and the idea of equivalence that JEE loves to test. Do not miss it. And so, my friend, we have crossed another chapter together. It may have looked like just a scale from 0 to 14 and one small equation. But understand this, ionic equilibrium quietly runs acid-base titrations, salt analysis, and half of qualitative inorganic chemistry that is still ahead of you. Sarah, David, Lisa, and John all sat exactly where you are sitting now with this very same class. Be patient with yourself. Revise the Henderson equation tonight, once, slowly, and let it settle. One idea at a time. You will crack JEE. Of this I am certain. If this class brought you clarity, subscribe to the channel so the next one finds you. Until then, keep going. I will see you inside Redox.